Welcome to Math TV with Professor V. In this video, we're going to learn how to find the power series representation for various functions. And this is one of the trickiest topics in calculus too. And what I think the easiest thing to do is understand that it only comes down to 3 different cases. You have to keep in mind that our home base, or like our safe place, is the function 1 over 1 minus x, whose power series representation is the sum n equals 0 to infinity x to the n. This is based on geometric series, right? So x is r, and we know that this series will converge as long as the absolute value of x is less than 1, strictly less than 1, which means the radius of convergence r is 1. This you have to memorize, okay? This is like home base, what I tell my students. From here, depending on what the function looks like, you're gonna do one of 3 things. If it resembles this enough, but maybe this term is a little bit different, there's some extra stuff going on in the numerator, all you're gonna have to do is multiply, divide, add, etc. Do some clever things to manipulate the original sum, n equals 0 to infinity x to the n, and you're done. The second case is if you have 1 over 1 minus x to some higher power down here. I don't usually start busting out the binomial series. What I do is find a power series for some version of 1 over 1 minus x, or whatever it may be, and then you differentiate. And then adjust. Okay, I'll show you what I mean by that in a minute. And then the third case is your function involves ln of something, right? So then what you're going to do is take the derivative, find a power series for the derivative, and then anti-differentiate that to undo it, integrate it, and adjust. You'll see what I mean. You'll see what I mean as we start working through. But there's really only 3 cases. So I think when you remind yourself of that, it will feel less overwhelming, okay? And we're just going to jump right in and do some examples. So if you're one of my students, I'm going to start off doing some easier stuff from the homework just to kind of like refresh your memory. And then we're going to work on the last few spicy ones from the practice test, okay? Here we go. So the directions are basically find a power series representation for the following functions. I'm going to do some out of the textbook, so we'll find the radius of convergence as well. Okay, great. So first one, we're going to start off really relaxing, okay? First one, f of x is 1 over 1 plus x. All right, what did I tell you home base was? You got to memorize this. 1 over 1 minus x is the sum, n equals 0 to infinity x to the n, and radius of convergence is 1. How can I make this f of x resemble that home base? Oh, well, it's not too bad. I already have a 1 in the top. I love that there's a 1 here. I just wish that plus x was a minus x, so I'm going to make it happen. I'm going to write it as minus negative x. And then how does that affect what I'm writing in my infinite series? Well, now I have the sum n equals 0 to infinity, and instead of x to the n, I'm going to have negative x to the n. Do you see that? Oh, good. And then no, you don't leave your final answer like that. You're going to split up the negative from x. So we write this as n equals 0 to infinity, negative 1 to the n, x to the n. You want to try to leave it so it's just x to the n at the end whenever possible. If we're going to find the radius of convergence, easiest thing to do is go to the step right where you first wrote your sum, because this is R, right? If we're thinking of a geometric series, and we require at this step, if you think back when you first learned geometric series, we require the absolute value of R, in this case, absolute value of negative x, which is just absolute value of x, to be less than 1. So that means the radius of convergence is just 1. And the interval of convergence, if anyone were to ask, is from -1 to 1, not including the endpoints. How do I know that? I didn't even do a ratio test or anything. I don't need to. Because remember, geometric series diverges if R is equal to 1 or -1. So I know for sure that these endpoints, 1 and -1, will not be included on the interval of convergence. I don't need to spend any more time thinking about it. This is only true for power series like this, okay? All right, good. That was not so bad. That was a warm-up. Let's do another warm-up. Example 2, f of x is 2 over 3 minus x. So this looks rather different than 1 over 1 minus x, but we can adjust. I can write this as 2 times 1 over 3 minus x, right? But then, I'm still not happy. I need a 1. This is a 3. How do I adjust? I divide out, or I factor out that 3 from the denominator. So this is 2 times 1 over, let me take the 3 out here. Nobody have a panic attack. And then this is 1 minus x over 3. Woo! Okay. Are we all right? Good. So basically, this is my R now. Okay. And I just have an extra 2/3 hanging out front. So I have 2/3 times the sum, n equals 0 to infinity, x over 3 raised to the n. Boom. If you want to find the radius of convergence now, go for it, or just remember this is the step to come back to right here, because we require absolute value of R to be less than 1, which means absolute value of x has to be less than 3. So my radius of convergence is 3. Interval is from -3 to 3. Okay, that's done. So let's clean up the series now. So you want to try to leave it as x to the n in the final step. So we have 2/3 sum, n equals 0 to infinity, x to the n over 3 to the n. And then it will be useful. Let's see how there's a 3 out here. Bring it inside the sum. I'm going to leave the 2 out, though. He has nobody to join with inside the sum, so just leave them out there like a little loner. Okay, x to the n over 3 to the n plus 1. That's it. Good? So we're still doing the first case where all it just takes is some, manipulation using arithmetic. Arithmetic, that's all we're doing. Okay, let's try another before I start upping the spice level. Okay, f of x is x squared over x to the 4th plus 16. So how are you going to make this resemble 1 over 1 minus x? First things first, I'm moving that x squared away, right? And then I have times 1 over. Why don't we write this as 16 plus x to the 4th? It makes me feel better when the constant's first. Doesn't it make you feel better? Other issue is I need this to be a 1. So again, like last time, let's factor out the 16. And then I have 1 over 1 plus x to the 4th over 16. Is this good? Can I write a power series? Not yet. Make that subtraction. So we have x squared over 16 times 1 over 1 minus negative x to the 4th over 16. Beautiful. Okay. So focus right here. This is your R. And then this stuff just hangs out, okay? X squared over 16. We'll deal with it later. Sum n equals 0 to infinity, negative x to the fourth over 16 to the n. Okay. Let's see. Do you want to find the radius of convergence now? Why not? Here's R. We know that this sum converges if the absolute value of R is less than 1, which would mean the absolute value of x to the fourth is less than 16. And that happens if absolute value of x is less than 2. So radius of convergence is 2, and the interval's from -2 to 2. All right, now let's clean up. So x squared over 16, sum n equals 0 to infinity. Now distribute the power of n to this negative, to x to the fourth, and to 16. So you're going to have -1 to the n, x to the 4n, over 16 to the n. Ooh, okay. And then let's go ahead and bring in what's on the outside. So we have sum n equals 0 to infinity, -1 to the n, x to the 4n plus 2. Why 4n plus 2? Because I'm bringing x squared inside the sum now. So if you have x to the 4n times x squared, that's x to the 4n plus 2. Okay, and then similarly, down here, you see, I have 16 to the n, and then I have one more. So then that would be 16 to the n plus 1. Now, you could stop here, but technically, like 16, we can break it down as 2 to the fourth raised to the n plus 1, and then that would be, remember, this would distribute 2 to the 4n plus 2. And the reason that's just a wee bit more desirable is because, well, 2 also matches the radius of convergence, and then notice this exponent is the same one that I have on x. So that is a more desirable way of writing it, guys. Yeah, I know. So we have the sum n equals 0 to infinity, -1 to the n, x to the 4n plus 2, over 2 to the 4n plus 2. Yes, box that one with pride. Job well done. Job well done. Okay, let's up the intensity just a wee bit now, okay? And we're gonna look at the following sum. Which one was this? Okay, number 4, example 4. This is gonna be a little different. 4a. F of x is 1 over 1 plus x squared. Ooh, this is the second scenario now, okay? Anytime you see an exponent down here, what you're gonna need to do is first find a power series for the plain version. Plain version being just 1 over 1 plus x. Then you're gonna differentiate the appropriate number of times to make that exponent. I'm gonna tell you something right now that I learned the hard way. You don't want to square an infinite series, okay? So don't say, oh, I'm gonna find the I'm gonna find the representation of 1 over 1 plus x, and then just square it. That sounds great. I know it sounds great, but it doesn't work out well. Okay, don't square an infinite series. I always wanted to. It never was the answer. And I'll tell you, if you're in Calculus 2, you're not going to need to. I'm not saying you're never going to need to in your entire math career, but it won't be necessary in this class. Got it? Great. Okay, so 1 over 1 plus x, we did that one already at the beginning of the video. Think of it as, 1 over 1 minus negative x, right? Right. So then this is the sum, n equals 0 to infinity, negative x to the n, which is the sum n equals 0 to infinity, -1 to the n, x to the n. And we know radius of convergence for this guy is 1. Great. So how am I going to make it squared in the denominator? Well, I want you to remember that 1 over 1 plus x is 1 plus x to the negative first, yes? So what we're going to do is take a derivative instead, okay? So the derivative with respect to x of 1 plus x to the negative first is going to be, let's see, so you take that exponent, bring it down in the front. So this is negative 1 plus x, and then subtract 1. My new exponent should be negative 2. And then we do have to just think about the chain rule. You would multiply by the derivative of the inside, but that's just 1. Great. Now I'm going to take the derivative, because I took the derivative of one side of the equation. Now I'm going to take the derivative of the other side. Don't be scared. Identify x. Where is x in the sum? It's just right here. Everything else is a constant, so don't mess with it. We're going to have the sum, negative 1 to the n, and then if you take the derivative of x to the n, it's going to be n times x to the n minus 1. You bring that exponent down in front and then subtract 1. That's your new exponent. Now, you have to be careful. Anytime you take the derivative of an infinite series, check that index. N starts at 0. If I plug in 0 for n here, you're going to have negative 1 to the 0, x to the 0, which is just 1. And that's a constant. So when I take the derivative of the n equals 0 term, it goes away. So my new sum is going to start at 1 to infinity. Let me write that out one more time because I feel like you probably are a little overwhelmed. I'm not writing out this whole sum, but the first term when n is 0 is 1. And then when n is 1, it's minus x. And then plus x squared minus x cubed plus x to the 4th, etc., right? This is n equals 0. This is n equals 1. And so if we take the derivative, boom, boom, well, this one's going to go away, right? So that's why the derivative starts at n equals 1. All right, good. So let's see, what have we done with ourselves? Are we in any better shape? Right here, this is negative 1 over 1 plus x squared. That equals the sum, n equals 1 to infinity, negative 1 to the n times x to the n minus 1. Is that what we want? Is that f of x? Let's look. Here's what I have a power series for. F of x looks super similar. It's just I got to get rid of this negative. Okay, so I'm just going to multiply both sides by another negative. And that's the same as just multiplying by negative 1 to the first, right? Why am I telling you that? You're like, I know. Because I can combine that extra negative with negative 1 to the n. So now I have 1 over 1 plus x squared equals the sum. N equals 1 to infinity. See how these two are going to combine? I have negative 1 to the n and negative 1 to the first. So that's negative 1 to the n plus 1 times n times x to the n minus 1. All right, and then you do want to try to have your final answer with x just to the n if possible. So let's see, if I want to make this n instead of n minus 1, I want that to go up by 1. So if I want this expression to go up by 1, I need to start the sum 1 lower. So I'm going to start at n equals 0 to infinity, and then now all of the n's become n plus 1's. So then I have n plus 1 plus 1, n plus 1, x to the n plus 1 minus 1. Okay, so anytime you lower the index here, you have to add to the expression in the sum by that amount. Now, notice, I have negative 1 to the n plus 2 over here, right? Well, that's negative 1 to the n times negative 1 squared, which is just negative 1 to the n, because that's positive 1. So let's clean that bad boy up. So n equals 0 to infinity, negative 1 to the n plus 1 times x to the n. Great. Now, what's the radius of convergence for this series? Well, before we took the derivative, we knew the radius of convergence was 1. And we have a fabulous theorem that tells us that the radius of convergence of a power series is preserved, or it stays the same, when you differentiate or integrate. So, thank you, theorem. I don't need to check a single thing. The radius of convergence is still 1. I know, and the theorem doesn't even have like a set name like mean value theorem or squeeze theorem, but I think it's so valuable. I love it. Okay, that was part A. Part B, are you ready? Let's get a little spicier. Part B, I want a power series for g of x equals 1 over 1 plus x cubed. Ooh. Remember, this is already a power series. Let's erase this. This is already a power series for 1 over 1 plus x squared, right? Which is 1 plus x to the negative second. So if I want to change the exponent in the denominator from 2 to 3, make it go up, take a derivative. So derivative with respect to x of 1 plus x to the negative second is going to be the derivative with respect to x of this glorious power series we just found, n equals 0 to infinity, negative 1 to the n plus 1, x to the n. Okay, let's see what emerges. So take the exponent, bring it down in the front. That's going to be negative 2. Leave that alone. New exponent's going to be negative 3. Good. And then derivative of the inside's just 1, so we don't need to do anything else. Now, we're going to have the sum. Be careful. When n is 0, the first term is going to be a constant. So when I take the derivative, it's going to go away. So the derivative needs to start at 1 to infinity. Don't have a meltdown. We're taking the derivative with respect to x. So everything besides x to the n is a constant. So it just comes along for the ride. Just rewrite it as is. And then now take the derivative of x to the n. You can do that. You just did it a second ago. Bring the exponent down in front and then subtract. Now it's x to the n minus 1. See, look at us surviving, thriving. We're fine. Okay. Now look what's over here on the left-hand side. We have negative 2 over 1 plus x cubed. Okay, is that what I want? Is that g of x? Not quite. Not quite, people. What's there that I want to get rid of? Well, I'm looking at g of x. There's just a 1 in the numerator. And here's a negative 2. But we can get rid of it. We can just multiply both sides by negative 1/2. Negative 1/2. I want to put it right there. Okay. So then this cancels. And then I have on the left-hand side 1 over 1 plus x cubed. And then this is going to be the sum. N equals 1 to infinity. I'm going to leave the 1/2 outside. But the negative, I will incorporate with this negative 1 to the n. Okay, so then we'll have negative 1 to the n plus 1, n plus 1, n x to the n minus 1. Okay, lovely. No, don't leave it like this, because we want to try, if possible, to have our final answer just have x to the n. So I want this to go up by 1. So I'm going to replace all of the n's with n plus 1. If I want that to go up, then I need to go the opposite direction. This needs to start at 0. So we'll be done soon. 1 over 1 plus x cubed is, just leave the 1/2 out there, right? There's no 2 inside to combine it with. Start at 0. We talked about this. This is going to become negative 1 to the n plus 2, but that's just the same as negative 1 to the n. This is going to become n plus 2. This is going to become n plus 1. Okay? And then you'll have x to the n. Wow, wow, wow. Here's this one. What's the radius of convergence? Should we do a ratio test? Heavens no. We found the radius of convergence of this guy, and it was 1. And all I did was differentiate and just mess with some constants, so nothing's going to change. So it's still 1. Okay. Last part to this problem, example C. Say I wanted you to find power series representation for h of x, which is x squared over 1 plus x cubed. What would you do? Well, I already have a power series for 1 over 1 plus x cubed. The difference is I need an x squared now. So I should multiply this entire sum by x squared. So that equals x squared times a half times the sum, n equals 0 to infinity, negative 1 to the n plus 2, n plus 1, x to the n. So I'm going to bring this and combine it with x to the n. So then now we'll have the sum, n equals 0 to infinity, negative 1 to the n plus 2, n plus 1, x to the n plus 2. Good. Should we adjust? Yes. I can write this as x to the power of n if I subtract 2 from all of the n's here. So if I want these to go down by 2, this needs to start 2 higher. So now I'm going to start at n equals 2. I know, kind of wild, huh? And then negative 1 to the n minus 2 is also the same as negative 1 to the n. And then this is just going to become n plus 2 becomes n plus 1 becomes n minus 1, and then we have x to the n. Very lovely. Radius of convergence is still 1, right? All I did was multiply by x squared. If you are too nervous, do a ratio test. Why not? Okay, so this is the second scenario. You have a higher power down there in the denominator, so you find a power series for the original without the higher power. Remember how we started in the very beginning, just with 1 over 1 plus x? You get a power series, and then you take the derivative however many times you need to keep bumping up that exponent, all right? Last case is they give you, I want to see what number that was, 4. So last case is they give you some sort of function that has a natural log in it. Like, why natural log? Because that's like the only other kind we can do, okay? We're running out of options. These are the only, and when you remind yourself of that, I think it makes it less intimidating. Like, there's only 3 scenarios, you guys. So here's the third one. F of x is ln of 5 minus x. No. Home base is 1 over 1 minus x, which is the sum, n equals 0 to infinity x to the n. I cannot get a ln of 5 minus x to resemble this in any way right now, okay? What we do is we take the derivative, always, f prime of x. So derivative of ln something is 1 over the something, and then by the chain rule, you have to multiply by the derivative of the something, of what's inside. So derivative of 5 minus x is negative 1. So let's see, this is negative 1. I'm going to put that in the front. Over, I'm going to factor out a 5 times 1 over 1 minus x over 5, right? Can we get a power series for this bad boy? Certainly. So we have negative 1/5 times the sum, n equals 0 to infinity, x over 5 to the n. If you want radius of convergence right now, let's do it. So we require absolute value of x over 5 to be less than 1, which means absolute value of x is less than 5. So radius is 5. Okay? Can we simplify this sum further? Yes. I'm going to bring in, leave the negative out because you see how there's no negative in here being raised to the n. It's not alternating. It's just like one lonely negative. He can stay outside. And then we have the sum n equals 0 to infinity x to the n over 5 to the n plus 1. Now remind yourself, who does this power series represent? F prime of x. Oh, okay. So we didn't quite do what we were asked. We found a power series, but not for the original function, for its derivative. How do I get back to the original function if I have its derivative? Well, you take an antiderivative, right? Also known as an integral, thanks to the fundamental theorem of calculus. Ba-boom, ba-boom. Please don't forget your dx. It makes me angry. Okay, so then now over here, we've got f of x equals. Don't be scared to integrate an infinite series, okay? I know it can be overwhelming, but just remind yourself, this and this are just constants because I'm integrating with respect to x. So focus on where x is because nothing else is changing, okay? In fact, just rewrite it right now so you stop stressing. This negative, keep that there, n equals 0 to infinity. When you integrate, you add 1 to the exponent, so it's going to be x to the n plus 1, and then you divide by the new exponent. And then I still have that 5 to the n plus 1 down there, plus c. Yeah, that's it, literally. Okay, how can I find c? Well, look at where the power series is centered. It's centered at 0. How do I know that? If it wasn't centered at 0, it would look like this. It would look like x minus 2 to the n plus 1 or something like that. You know what I mean? Over blah, blah, blah. That's when it's centered at x equals 2. So then you would plug in 2 for x. You want to plug in whatever value of x will make every single term in this sum 0. That way it goes away and you can solve for c, okay? So in this case, that number is 0. Most of the time it is 0, you guys, okay? So f of 0 equals the sum of 0 plus c. And how does this help me find c? Well, I have f of x right here. F of x is ln of 5 minus x. So f of 0 is ln of 5. So that tells me c equals ln of 5. So then now I can write f of x is negative sum n equals 0 to infinity x to the n plus 1 over n plus 1, 5 to the n plus 1 plus natural log of 5. Can we clean up? We certainly should. I can write this as x to the n if I start at 1. So let's do that. So then f of x is, it would look better. Let's put the ln of 5 first and then the minus sign. Like, hopefully at this point you have some aesthetic appreciation, right? That like starting with the negative is not cute. N equals 1 to infinity, and then we have x to the n over n times 5 to the n. Radius of convergence is 5. Wow. Do you feel fancy? I asked my class the other day, I'm like, did you ever think you'd be integrating an infinite sum? Be proud of yourself. Look at where you are. Okay, so that's the third scenario. You have ln, and you're like, whoa, so I'm going to take the derivative first, find a power series for the derivative, and then integrate that power series so you can have a power series for the original. Okay, great. So from here, what I'm going to do is a couple from the practice exam, so my students can be excited. Here we go. Same directions. I think this is number 6. Again, f of x is 1 over 1 minus 6x squared. Okay, which scenario is this? Can I just manipulate algebraically, multiplying and dividing? No. Since I have this exponent here, what I'm going to have to do is first start with a power series for 1 over 1 minus 6x, and then I'll take its derivative to bump up that exponent. So power series for 1 over 1 minus 6x is going to be the sum, n equals 0 to infinity, 6x to the n. So 1 over 1 minus 6x is the sum, n equals 0 to infinity, 6 to the n, x to the n. All right, great. Is that what we want though? No, I need the denominator to be 1 power higher. So I'm going to take a derivative. I'm going to rewrite this though as 1 minus 6x to the negative first. Okay, so the derivative with respect to x of 1 minus 6x to the negative first. So bring the exponent down in front, subtract 1, and then this time when we do the chain rule, what's the derivative of the inside? It's negative 6. Very good. This equals the sum. Now be careful. The first term, when n is 0, is a constant. So when I take the derivative, it's going to go away. So n has to now start at 1 to infinity. Only x is my variable, so 6 to the n just hangs out. When I take the derivative of x to the n, it's n times x to the n minus 1. Okay. So let's see, what is this? If I clean it up, it's positive 6 over 1 minus 6x squared. This is the sum. N equals 1 to infinity, 6 to the n, x to the n minus 1. Is that my f of x? Is that u f of x? No, not quite. Look at this 6. It need not be there. So how do we get rid of it? Very good. Multiply by 1/6. 1/6. So then now, woohoo, we have 1 over 1 minus 6x squared, and this equals the sum. N equals 1 to infinity. Watch this. I have 6 to the n divided by 6 to the first. So that's going to be 6 to the n minus 1 times n times x to the n minus 1. And no, we don't want to leave it like that. I want x to be raised to the n. So if I want this to start at n and I want to add 1 there, I got to start 1 lower. So we'll start at n equals 0 to infinity. And then we'll have 6 to the n times n plus 1 times x to the n. And that just looks weird to me, so I'm going to put the n plus 1 first. Isn't it looking ugly? Oh no. N plus 1, 6 to, that's better, yes. And then I'll just say this equals f of x. Okay. Beautiful. Beautiful. Okay, I got another one for you. This time it's going to involve ln. I don't even know what number I'm on. Okay, I think 7. F of x equals x squared ln 1 plus 4x. Ooh, okay. Don't worry about this x squared till the bitter end, okay? First, we're just going to start with ln 1 plus 4x. Can you find a power series for this? No. We take the derivative first, and then we'll find a power series for it. So the derivative of ln of 1 plus 4x is 1 over 1 plus 4x times, don't forget the chain rule, times 4. Okay, so that's, let's see, 4 times 1 over 1 minus negative 4x, right? You see where this is going? Good. So this is going to be 4 times the sum, n equals 0 to infinity, negative 4x to the n. Let's clean it up. So that's 4 times the sum, n equals 0 to infinity, negative 1 to the n, 4 to the n, x to the n, and then we should combine these 4's, right? Good. Okay, so then that's the sum, n equals 0 to infinity, negative 1 to the n, 4 to the n plus 1, x to the n. And this is the derivative of ln of 1 plus 4x. Well, how do I get back to ln of 1 plus 4x? This is a power series for its derivative. To undo a derivative, we have to integrate. So then now, if I integrate the derivative, then I just get back ln 1 plus 4x. And then here's where I have to always just give you a little pep talk. I know there's a lot of scary stuff going on, but this is the only x in that integral. So everything else just stays the same. It doesn't change. It's just a constant. N equals 0 to infinity. Negative 1 to the n. 4 to the n plus 1. Add 1 to the exponent. Divide by the new exponent. And we pick up a plus c. Good. See? Okay, now from here, we have to find c. So where is this power series centered? At 0. Remember, if it's not centered at 0, it would be like x minus or x plus some number in parentheses. I don't see that. So I'm going to plug in 0. So I have ln of 1 plus 0 equals the sum of a bunch of zeros plus c. So ln of 1 equals c, which is 0. Okay. So that means now I have ln of 1 plus 4x equals the sum, n equals 0 to infinity, negative 1 to the n, 4 to the n plus 1, x to the n plus 1, over n plus 1. Okay, good. Good. Is that what we wanted though? Not quite. I have a power series for ln of 1 plus 4x. What's missing? X squared. I told you save it for the bitter end. This is the bitter end. So I'm just gonna go ahead and multiply both sides now by the x squared. Okay, and one mistake I saw a lot of my students do yesterday, they wanted to put it in too early. I think it just makes it more confusing, okay? I would wait until the very end to just multiply by extra stuff. So then we have x squared ln 1 plus 4x equals the sum, n equals 0 to infinity, negative 1 to the n, 4 to the n plus 1, x to the n plus 3 now, over n plus 1. Okay, do we want to lower this by 3 and start this at 3? This would then become n minus 2. I don't think so. I would say let's just start at n equals 1, and then this is a kind of rare case where it probably doesn't look better to have x be to the n. So now I'll have negative 1 to the n minus 1, 4 to the n, x to the n plus 2 over n. So what did I just do? I started the index 1 higher, so then I have to subtract 1 from all of the expressions involving n here. I think that's the cleanest way to write it. Let me show you. If we were to try to have x be to the n, then I would need to, excuse me, maybe this is not, okay. If you wanted to start at x to the n, then you would need to start the sum at n equals 3. And then you would subtract another 2. Ooh. So I would have negative 1 to the n minus 1 minus 2, which is n minus 3. That's negative 1 to the n times negative 1 to the negative third. That's negative 1 to the n. This is still just negative 1, right? So you could write it as negative 1 to the n plus 1 or n minus 1. It doesn't matter. Then 4 would be to the n minus 2, and then the denominator would be n minus 2. I don't think that looks better. You know, this matching looks better than having this extra chaos. So I would say just stop here. This is like a rare case where it's better to just leave it as n plus 2. But check with your professor. Whatever they want, make them happy, literally. Okay. Last one, it's a fun, spicy one, okay? Yes, I think I called that one 7, so I'm calling this one 8. Where did it go? Here it is. F of x is ln 1 plus x cubed over 1 minus x cubed. Okay, so when you see ln, you go, ooh, I'm not going to try to find a power series with this guy. I'm going to take the derivative first. And I'm not going to just jump right in and take the derivative right now because I would have to do such ugly chain rule, right, involving the quotient rule. So I'm going to use my log properties and write this as ln 1 plus x cubed minus ln 1 minus x cubed. So now let's take the derivative. So derivative of ln of something is 1 over the something times the derivative of whatever the something is. In this case, derivative of 1 plus x cubed is 3x squared. Minus the derivative of the other term is going to be similar. 1 over 1 minus x cubed times negative 3x squared, right? That's the derivative of the inside here. There's its derivative. So what does this turn into? This turns into 3x squared over 1 plus x cubed plus 3x squared over 1 minus x cubed. And this is f prime of x. Now, you could try and get a power series for each of them right now. And then there's a way to combine them into one sum. It's just a little more work. What's easier is to combine them right now. And this is a special kind of case where it works out nicely because you see how the denominators are conjugates? It's going to turn out so pretty, watch. So I'm going to clean up and get a common denominator. So I'll multiply this guy by 1 minus x cubed, top and bottom. And then this guy by 1 plus x cubed, all right? So now we have 3x squared minus 3x to the 5th, I'm just distributing, plus 3x squared plus 3x to the 5th over 1 plus x cubed times 1 minus x cubed. And the cool part is, see how these 3x to the 5ths just cancel? Good. So then f prime of x is 6x squared over, if I multiply out the denominator, what do I get? It's 1 minus x to the 6th. You can find a power series for this really easy, can't you? Yeah, it's just 6x squared times 1 over 1 minus x to the 6th. So then that's 6x squared times the sum, n equals 0 to infinity, x to the 6th to the n. Oh, and then this is 6x squared times the sum, n equals 0 to infinity, x to the 6n. And then we're almost done. This is 6 times the sum, n equals 0 to infinity, x to the, I want you to combine these right now, 6n plus 2, right? Good. And this is all the power series for f prime of x. Good. The worst is over, I promise. So now how would I find a power series for f of x? I have one for f prime. How do I go backwards? Integrate. Integrate. Okay. So then f of x equals, no panic attacks. Just add 1 to the exponent, divide by the new exponent, leave everything else alone. Leave it alone. 6 times the sum, n equals 0 to infinity. Add 1, it's going to be x to the 6n plus 3 divided by 6n plus 3 plus c. Yeah, don't forget the plus c. We're going to solve for it really quickly. This guy's centered at 0, so I'm just going to plug in 0 for x. So f of 0 equals 0 plus c. Do you remember what f of x was? The original? It was ln 1 plus x cubed over 1 minus x cubed. So f of 0 is ln 1 plus 0 over 1 minus 0, which is ln of 1. So that's 0. So c is 0. How boring. I'm sorry. Okay. Now we can put it all together. So f of x is 6 times the sum, n equals 0 to infinity, x to the 6n plus 3, over, I can factor out a 3 from here. And then I have 2n plus 1, don't I? And last I checked, 3 and 6, that can cancel. And I just have a 2 here now. Wow. So f of x equals the sum, n equals 0 to infinity. Where'd the 2 go? It's right there. X to the 6n plus 3 over 2n plus 1. All right, there you go. If you can do all of these examples again on your own, I think you're set. I think you're set. And then explain it to somebody else, and then you've got it down packed. That's literally the best way to study, is to explain something to somebody else. So even if you have no one to help, if your classmates don't need you to explain, just talk to yourself, talk to your mailman, talk to your massage therapist, talk to your barista, talk to somebody and explain to them how to find the power series representation for different functions. And there's only 3 scenarios. Remind yourself of that, and it should be less wild. Okay, if you made it to the end, leave me a comment down below. Tell me. I'm a trooper. I made it to the end. Give the video a thumbs up if you found it helpful. Subscribe to my channel if you haven't already. I have full video lectures for all of the sections in Calculus 1, 2, and 3 from when I teach my classes on my YouTube channel. It's organized into playlists. And then for my members only, I have videos on differential equations, linear algebra. If you want like extra practice, extra worksheets, exclusive videos, you can join my Patreon. Everything's ad-free there. Lots of stuff that's not on YouTube. And you can also catch me on Instagram and TikTok at MathTV with Professor V. Thank you guys so much for all your support. I appreciate it. I know this stuff is hard, so just keep up the great work. All right, talk to you later. Bye.